Record. It's recording right now. Okay. Share the screen. Okay, now we're back. So since I just started recording the video, let me repeat it again. This is the concrete 7 days and 28 days data. You will get this in front of you once you pull up the file. So if you look at the concrete handouts, you will see a couple of equations and you will see some graphs in front of you. And this is the handouts that was for the theory. But I think we can look at the equations over here on this report. This is the first equation that we're going to use to calculate the stress, compressive stress applied on the concrete specimen. We need to use the applied force, which we measure during the testing. We measure the applied loads with the corresponding deformation. And we need to calculate the cross-sectional area to solve this equation. And cross-sectional area is already calculated for you. And this is pi d or pi d squared over 4. We also measure the length of the specimen before the experiment, and we will use it to calculate the strain. This is the second equation. You need to have the deformation due to the applied force, which is on this column. And then you need to know the initial height. And we measure the initial height, 12 inch. Has anybody checked the slump? Was it 3.5? Noah or Patrick?
I'm still looking through my notes trying to find it. I remember I wrote it down somewhere.
Okay. So let's look at this first calculation. We have the applied force, 9,857 pounds, divided by the cross-sectional area, which will be constant throughout the calculations. So I see that the first cell is 348.8 psi, and I will run this all the way down, and I will get 4,302 psi or 4 ksi for 28-day compressive strength. And we were expecting to have 4,000 psi. And if you don't remember why we were expecting 4,000 psi, because of the concrete specs, because of the advertised compressive strength of the cement we used. So we were expecting slump.
Was the slump going to be on the concrete handout that we got before the midterm? Because I'm looking through my notes. Okay, I just wanted to make sure.
Right, because we did the slump test
right
in the first class of the concrete, and then we noted that it was, I believe it wasn't the first time, it wasn't in range, and we did the mix. We had more sand and cement, and I believe it was 2.75. I remember it was 375, but after I seen this slump range, I believe it was 2.75. But anyways, the 7 day.
2.5 inches.
What was that?
2.5 inches.
2.5 inches. So I'm going to put 2.5 inches over here. So when you are working on your report, you can just fill this blank, because on your data sheet, slump is not provided.
Can you go just click on that first cell that you did, just so I could see the equation? Because
Zoom in.
Yeah, I was I forgot to put the dollar sign.
Yep. Once you put the dollar sign, it just locks this cell. So the cell doesn't change. Only variable changing in this equation is load column. So with that being said, we got the stress column. And next, we're going to use the second equation that we were checking out earlier. Here, deformation due to applied force over initial height. And again, 28 days is 4,000 psi. That's what we were shooting for. And we got more than 4,000 psi. Because this brand Quick Grip, they want to be on the safe side and they use factor of safety. That's why it's coming more than 4,000 psi. And if you use less cement, obviously you're going to lose some strength and it will be less than 4,000 psi. Or if you add more water, but if you follow the procedure, you should get at least 4,000. This is the minimum that we are expecting. Okay, so we're looking at this equation and let's do the calculation.
Will we have to include that in the report of the factor of safety for the pressure?
Yep, for the stress, yes.
Stress, yes.
Mhm. Pressure is used for the liquids and stress is used for for solid materials. That's okay. Strain calculations. Let's go with the first one. So the formation is 0.01 inches and the length is 12 inch. This is the gauge length. Doing the same procedure. Calculate the first one. I go all the way down. When you go all the way down, you're gonna see 0.0 here because we don't have the measurement for the deformation that's corresponding to the maximum applied load. Because if you see in the video, you take the compressor emitter out of the specimen before it breaks, because if you don't take it, it just crash and damage the entire compressor emitter and the measuring device, measuring gauge. So that's why we don't have the deformation measurement at the end of the experiment at the failure. So you're gonna manually get this deformation from the graph, and I will explain to you when we get to the graph section. Let me make it more specific. Manual. Okay. And for 7 days, you'll basically do the same thing, copy and paste, stress and strain calculation. You see that at the end of the 7 days, you reached 2,200 PSI, and we were expecting 2,500 PSI, probably due to the curing conditions on that time or for some reason that I can't think of. Probably it's the curing condition, temperature, or the humidity affected. And I believe temperature or humidity conditions came to the perfect condition after 7 days. That's why we exceed 4,000 psi, and it got up to 4,300 psi. But at 7 days, we are below the compressive strength that we were expecting. This is what it tells you. And for strain, again, you use the overall length, gauge length. Same way you will provide. And if you look at the handouts, one second, concrete receipt. I don't have the concrete handouts here, but let's look at this report. There you go. So the final strain value is manually determined from graph, because the graph cannot be constructed without having these data points, but you use the forecast method. So this graph automatically calculates and forecasts where will be the strain at 2200 psi, for example. In this case, it's, I believe, 2200 psi. And for 28 days, it's around 4300 psi, 4299. And again, manually, I draw a straight line corresponding to 4299 psi. And if you draw a straight line 90-degree vertical to x-axis, you can read the strain value. And if you get the strain value 0.018, you can go back to your report, your calculations, this. 0.0018. Let's see one more time. 0.018. I can determine what is the deformation based on the strain data that we read from the graph. So I'm going to use the same equation. Strain equals to length. This equation right there. This one. So now I know the gauge length. I know the strain. I'm going to solve for deformation. (0.0216). Let's go back to the graph. Once you get this graph and get your strain number, you can go back to your spreadsheet and calculate the deformation. Any question on the calculations so far? April?
Nope, I think I'm good.
You're good. What about Noah? Since I have 18 students, let's go one by one.
I'm good.
Okay.
Makes sense there.
Okay, I have more students. I can go one by one. But let's continue that. Did I explain this graph, how to develop the graph on the YouTube video?
Yes.
Yes, right? Okay, so you can watch that video again, because it will take quite a bit of time to develop the graph from scratch for me in this spreadsheet. But use the step-by-step procedure, and pull up the video to develop these graphs and how to read the strain and how to use the forecast option on the graph. Once you use the forecast option, it will show you where the trend line, where this graph is trending, and you can draw your lines to calculate, to determine the strain corresponding to maximum compressive strength. With that being said, you have data points already calculated. You just need to run this calculation one more time. And Young's modulus is the last one that you need to calculate. Like I said, there are two ways to calculate the Young's modulus for concrete. One way is to use the EACI method that's developed by American Concrete Institute. The ACI stands for American Concrete Institute. Equation was 57,000 square root of F prime C. Of the equation, but let's check it. It's actually 57. There you go. But let's confirm this equation again from this report. Let me see if it's mentioned here. But if you have the handwritten handout, I'm sure you'll be able to see that equation by ACI. Let's see ACI. Nope, this is not the information I was looking for. But since I run this calculation before, and this is the equation that I wrote here, and in the equation in the cell, that's the equation that I was looking for. And if you look at the handout, you will see that. So this is the first way to calculate the Young's modulus for the concrete. There's another way to determine it, and it's from the graph. And let's look at this one first, and then let's see what we're gonna get from the graph. So you type the equation, this H20 corresponds to maximum compressive strength for 7 days, and square root of this number, and I divide it by 1,000 to get it in KSI. If you don't divide by 1,000, it will give you the number by in PSI. So in 7 days, our Young's modulus for this sample was 2,677 KSI. For 28 days, it was 3,739. Once you calculate this number, you'll compare these two numbers with the one that you will get from your graph. Okay. You can only calculate the Young's modulus from the graph in the elastic region. So the elastic region is determined in this concrete report or concrete compressive strength stress strain graph. You use the F prime C, maximum compressive stress, and divide that number by 2. And you come to your graph and mark it on your curve. Once you mark that number, below that number is the elastic region, and above that number is the plastic region. So you can use any number, any points along the curve up until f prime c over 2. And you can calculate the Young's modulus by using the equation E for concrete stress divided by strain, same way that we calculated for steel. And it's only applicable okay. And to determine elastic region on the graph, you need to calculate f prime c over 2. So let's do the example with the number that we have. For 28 days, for example, f prime c is 4,302. Divide that number by 2. C over 2. So you get this number, 2,151 psi. And then you go back to the graph. So 2,100 and some decimals, 2,151. It should be around here somewhere. In your, when you develop your spreadsheet and your graph, you can zoom into your graph and you can be more accurate by selecting your data points on your y-axis, which is your stress axis. You're going to draw a line. This is for 7 days. We're going to look at the 28 days. My bad. This is orange curve is the 28 days. So you're going to come to 2100 somewhere here. Draw a straight line, and then below this point, this is linear. And you can even tell from the graph, this is a linear section, small linear, and we assume that it is linear. If it was perfect linear, slope should be the same, but you will see that slope is not the same in this region, that it slightly changes. So from this linear portion of your curve, you will pick 2 data points. So for 28 days, say 2150. There you go. So these numbers are smaller than 2150. Everybody agrees, right? Austin?
Yes.
Okay,
Yes, sir.
so this highlighted section, that's the elastic section, linear portion of the graph. So any points that I select in this portion, that will work. So stress divided by strain. Okay. Also, this says in KSI, but I have to divide that number by 1000 to keep the units in KSI. There you go. Like I said, if the line or curvature or whatever you name it, if it was perfectly linear, then the slope should be the same, but this is not perfectly linear. You see that this number is off by 600 psi. But these numbers quite close, and we agreed on that. Everybody is good at this point, right? Jacob, because this is the tricky part. Jacob Seal,
Yeah.
did you understand this part?
Yeah.
Okay. So you can either take the average of these close numbers, or you can select one of them. As long as you select your Young's modulus value in the elastic region, which is not often the average, because if I take the average of these numbers, it will tell me what is the average Young's modulus. I'm not going to include that first one and the second one. Actually, I'm not going to include the first one and the last one. We were quite close. All I'm trying to do, I'm just trying to be more accurate, because I can tell obviously this number is so off. So I got the average 3,384. I can call this as my Young's modulus at the end of 28 days. You see that this number is off compared to one we got from the ACI equation. And the reason for that, this is the real test, and we just only test one specimen instead of testing multiple specimens and getting the average. Imagine you test more than 100 samples with the same mixing conditions, with the same curing conditions. Temperature is the same during curing, and humidity is the same. And you use the same cement water ratio, then you should expect the same maximum compressive strength at the end of 28 days for each sample. But it is not the case. Always you're going to have numbers off than others, and then your job is to calculate the average and then the standard, calculate the standard deviation, how much each test deviates from the standard. So on your report, at the end of your report, on the discussion and conclusion part, you will mention why these two numbers are different than other. If we can use this equation test given by American Concrete Institute, why we got the different number from the concrete test. What else you need to mention in this report? Let's go back to sample reports. Yeah, if you don't calculate the modulus of elasticity for 7 and 28 days, you will receive, I will take off 5 points. But if you follow the same procedure and same format, you should be fine. Any question on concrete? If not, we're gonna go to beam bending.
Would you like us to include the images that you have on this report that you're showing us?
No. You're not gonna use any images from this report, but you can get screenshot from the concrete video that is on YouTube, or you can include, if you want to include any type of images showing the deformation of the concrete or the testing procedure, you can use different sources. You can include video from, like, screenshot of the video from YouTube when they're testing the concrete, because they use the same equipment that we use for concrete testing. But You shouldn't be using the same pictures from this report.
Okay, thank you.
Okay, no problem. Any other question? No. Okay, that's good. So this is the data for your report, and I will add the submission link. So if you can tell from the title, it's due on the same day of your final exam. Like I said at the beginning of the lecture. And please submit in one PDF format. Since I haven't scheduled the final, I'm just gonna make it first week of May. Let's say the second week, just to be on the safe side. May. And once I schedule the final day, final exam, I will change this due date. Perfect.
When we submit the concrete paper, do we put the Excel sheet and also
No.
the
No. I say it on the section. Let me see.
just want the Excel stuff to be included in the report as a PDF, right?
Please submit in single format. No exam. No. I believe this is more clear right now. For the Excel spreadsheet, it's just for yourself, for your calculation. It makes it easier for you to get faster on your calculations. And you just need to copy and paste the data points, your table. You can copy and paste the same data table. This is table 1, 7 days, and this is table 2, 4, 2, and 8 days. And you're going to include the expected F prime C. You're going to include the Young's modulus calculated by EACI equation, and you're going to include one more table that's going to show the modulus of elasticity calculated by using the graph. And you will need to have only one graph, not multiple graphs, like is shown here. So these are superimposed. You can have two different curves in one graph. You can select multiple data points for a graph. Like I said, I believe I mentioned this. I went over the graph development on my previous video on YouTube.
Yes, sir.
So with that being said, this is perfectly done. And I believe there is no question mark on this one. Okay. And this is already highlighted for you. You don't have to figure out, if you don't have time, you don't have to read the entire PDF, but this is really highlighted sections are really important for you. Just skim through what I mentioned here, especially if you're a civil engineer and if you're planning on working on construction. That's what I do every day. Concrete. Okay. You can also use this one. You can copy and paste as long as you use citation from this specs. You can include the concrete receipts, why it's important, and what are the key points that we look in the concrete receipt. Okay, time, for example. Time is important. What time it left the facility. Not bad. Should say somewhere. Okay. A job. So it left the facility at 12:20, 12:18, and it was at the site at 1 p.m. And you have 90 minutes timeline. If you're over 90 minutes, your concrete is not accepted. It's not qualified for the pouring. And you see the slump. Slump is important. And the type of concrete, 3000 psi. So you can mention this as well. So all the necessary things that needs to be on your report is here. All you need to do is just summarize these resources and spend more time on the concrete compared to any other report that you have done so far or you're going to be doing in the next few days, a few weeks, because this report is basically the entire test. Concrete test is 3 phases. So we spent 3 leg class on the concrete, and it weighs more than in other reports. And I believe I mentioned that before. It should be 30% of overall your report grade. Let's go to midterm exam. I will answer a couple of questions. If you guys have questions, I will give you the answers, and we can talk about the midterm a little bit. And if you have concern about your midterm grade, you can stay after this meeting, and I can answer your questions, and I can look at your paper. So the first question, explain the difference between ultimate tensile strength and the fracture tensile strength. That was pretty easy. You should remember the graph that we were working on the tensile test. You have stress strain graph, right? We have linear portion, elastic portion, and then we have the plastic region, plastic portion of it. And let's look at that graph really quick. In the meantime, who wants to answer the first question? Simple. Let's see. Perez, Yelitsa Perez.
Yes.
Okay, you are the lucky person. Can you answer the first question for me? Simply, what is the difference between ultimate tensile strength and the fracture tensile strength? You can just say one word, and I'll let you say.
The ultimate tensile strength is the maximum resistance.
Mm-hmm.
And the fractural tensile strength is just the final stress that will withhold the object and it breaks.
Yes, I know exactly what you mean, and you are right. You don't have to be grammatically correct or politically correct. So this is the ultimate tensile strength, right? So the difference between ultimate tensile strength and the fracture strength. Ultimate tensile, you can tell from the name, that's the maximum tensile strength in this that the specimen can take during the service condition. So this specimen, the steel sample that we tested, imagine it's for the beam that the beam that you design is made of the same specimen that we use. You know that from this graph, the ultimate tensile strength, the maximum capacity for this steel specimen is 73.77 KSI, and you know that you don't want to go beyond that number. And if you go beyond that number, your material, your member beam is going to fail at 51.93 KSI. You might say why this material doesn't fail at 51.93 KSI right here before it even reaches the ultimate tensile strength. I want one of you guys give me the answer for that. Why the steel specimen did not fail at 51.93 KSI before it even reached the ultimate tensile strength of 73.77 KSI. Did you guys understand the question? Patrick? Bouquet?
Can you repeat the question, please?
Okay, the question is, I see that from the graph, the ultimate tensile strength is 73.77 KSI, which is greater than the fracture strength of 51.93 KSI, correct?
Mhm.
Okay, my question is why this specimen did not fail at 51.93 KSI, which is right here, before it even reached to ultimate tensile strength of 73.77 KSI.
Because it started stretching.
Exactly.
And then, so the peak of the graph is where it really starts stretching the most, and then it needs less applied load as it stretches more.
That's
Basically,
correct. That's correct. Perfect. That's the answer I was expecting. So you see that over here, right after you reach the your yield strength, you see the plateau over here, and then you see the graph is keep going up. Trend is going up. It means material is gaining strength. This region is also called strain hardening. Materials it gains more strength because you can tell when they are processing steel, they have cold roll or hot roll steel, different type, and they have different procedures like quenching, giving heat, and deforming the steel. When they are making the swords back in the time, they were using high temperature and they were quenching the from hot to cold. They heat it up first when they're making the sword, and then they put in the cold water, and then they start hitting. When they hit the sword, what happens? It gets deformed, but it gains more strength, so it can handle more stress in the service condition. So the first question was super simple. So if you answer that first question like we explained, then you should get to 5 points. Second question, why do we test the concrete compressive strength after 7 days of casting and then again after 28 days casting? We just explained this, we just finished the concrete, and this question was also easy. I will let Tere to answer this question.
Yes, well, because the concrete gained 75 strength in 7 days, and then in 28 days, they permit to remove all. I don't remember, but I
Yeah.
remember that.
Yeah, you're on the right path. Basically, to wrap it up what you say, thank you, by the way.
Okay,
Uh,
you
7 days and 28 days. It's 7 days, you
Yes.
reach about 65% of your 65 to 70% of your overall 28-day strength.
Yeah.
And this is the regular procedure, 7 days and 28 days. This is what is being done on the concrete lab. But you can also predict with
Yeah.
the
3 to 7 days.
70% using the percentage. You can even get the 28-day result forecast by using the 3 days. You can test the concrete synthesis in 3 days, and you can use the forecast method to determine what the 28 days, because in reality, if you want to put it in perspective, let's say you are the construction manager and you want to go faster and be ahead of your schedule. You don't want to wait 28 days to get your concrete results to go to second floor, for example, if you are working on the multi-story concrete structure. Does that make sense? So you get your result in 3 days, and that 3-day result is also giving you the 28-day forecast. So you know, based on the statistical calculations, you know that plus or minus, let's say 5%, you will get a minimum 4,000 psi. Once you get that okay from the concrete lab, then you can proceed. You can remove your forming concrete forms, and you can continue your construction process. Is that
I'm sorry.
okay? Is that clear for everybody?
Yeah,
I have. Okay, yes. Go ahead, Tere.
Go ahead.
Okay, I'm sorry. I have a question. To use a high strength cement, instead of 28 days, you say that the 3 days, it's exactly 3 days, so it's in between 3 to 7 days, or it can be a little more or a little
Well, there
less.
are admixtures that you can use, and you can even get the 14-day strength overnight.
Oh,
Let's say you are working on the highway construction. There is a bridge that is damaged, and you are going to pour concrete, and your job is to open the traffic overnight, because the nighttime the traffic is low, and the daytime traffic is much more heavy. And on that type of problem, if you see that type of problem, what you do, you order the concrete with the specific admixtures added into it. That gives you the 28-day strength in overnight or in 2 days. There is no spec. It depends on the mixture. I can't give you exact numbers, but I can pull up from Google right now, and it will tell you how long it will take for a specific admixtures to get the 28-day strength.
For the concrete, I
One
remember
second,
you said something after the 20.
John, give me 1 second. I will answer your question. Give me 1 second. Let me pull up something. Give me 1 second. Well, this is for high strength concrete, and if you use silica fume, you can get up to 20,000 psi and compare this 20,000 PSI with 4,000 PSI that we were shooting for. 20,000 is pretty high, imagine. And the early strength development, that's what we're looking for. Water reduction, set acceleration, this is what we're looking for. It doesn't give you the exact time over here, but you can call Quikrete customer service, or if I find it tonight, I'll let you know what type of admixtures commercially available to gain the maximum compressive strength in a few days. I know that overnight is possible because I have friends working in DOTD, Department of Transportation, and they use admixtures in their concrete mix to get the overnight maximum compressive strength. John, let's continue with you.
Oh no, you just answer it. That's it. Thank you.
No problem. No problem. Let's go to.
I have a
Bob.
question.
William user. What's your name?
Rami.
Oh, Rami. Oh, Rami. Awesome. Hey.
Sam. Okay, so I was thinking the humidity chambers, do they help make them mature faster, or is that just like a constant to keep for the concrete to cure as opposed to curing outside the humidity chambers?
Now, this is the hard question that I wasn't expecting. Humidity chamber. I haven't used humidity chamber. I'm looking at it right now. How does it work? So as far as I know about humidity and the effect of humidity on the concrete, I know that if you have the perfect conditions, perfect curing conditions, I don't know the exact humidity measurement that you need to have to get the perfect conditions. That increases your overall strength of your concrete because it enhances the concrete chemical reactions, and it keeps the concrete hydrated during the curing. That's the number one that we want to have. Keep the concrete moist throughout the curing. So going back to your question, if you repeat one more time, if you direct your question, I will try to give you an answer. Rami, go one more time.
Yeah. All right. So when I worked at LSU, they have the DOTD lab, the concrete, and part of it was putting the samples after we make it. We put them in this humidity room. It looks like a big. I don't know if you ever seen like a walk-in freezer.
They used to have it. We still
But
have
I'm
it,
not
but
sure.
we don't use it. Go ahead.
I'm just not sure what the purpose for what we did that for was. Like,
Oh.
was maybe it's something like you were saying, like speeding up the process.
Exactly. That's humidity.
But you kind of answered
temperature room. That's what I answered. It's exactly.
Yeah.
When you say humidity chamber, I was assuming something else, but I know the humidity and temperature room, the curing room that we used to put our samples. It's in geotech lab, and if you guys know Late, he's another PhD student teaching geotechnical lab, and he knows where the humidity room, or if they have changed it right now, I don't know. It's been a long time I haven't visited that room, but in that room you set the humidity and temperature. So throughout the 28 days, humidity and temperature stays at the perfect conditions. Let me pull up what is the humidity or the temperature. What is the perfect temperature? Temperature. Concrete. Okay. It is advised that the concrete to be cured at a moderate temperature between 50 Fahrenheit to 90 Fahrenheit. So in the temperature room or the humidity room, you keep the temperature between 50 to 90 Fahrenheit. And I mentioned that before, a couple of years ago when we had freezing temperatures in New Orleans, we used to wrap the concrete with a tarp, with the plastic, to keep the temperature and to keep the temperature same and low higher than the outside temperature, just for the curing conditions. And I'm going to check the humidity too. One second. What is the perfect humidity conditions? This way I answer all the questions. So based on the ACI, American Concrete Institute, you need to have minimum 80 to 85% relative humidity for hydration to take place. So my first answer to your question was pretty much the overall answer. The current the humidity chambers, it's used for concrete to cure at the perfect curing conditions. So that humidity chamber keeps the temperature at a certain rate and the humidity at a certain rate. In this case, humidity is 80 to 85%. And what it does, it obviously positively affect the overall result, compressive strength result from your concrete sample. If you don't have the opportunity to keep your concretes pour on the job site at the lab condition, which is not never the, I never seen that case, because you are out there on the site, you can keep the temperature at between 50 to 90 Fahrenheit, or you cannot keep the relative humidity between 80 to 85%. But what you do is you also have the curing compound, concrete curing compound. That's what we use all the time when we are working on concrete pavements or concrete sidewalks. Especially right now, I work with the sewage and water boards. We do pavements and drainage work. We use the concrete curing compounds. As soon as we pour the concrete, curing compound is applied to keep the concrete in good condition against shrinkage and deformation. You got your answer, Rami? Rami?
Oh, yes, sir. Thank you.
No problem.
I appreciate that.
Would you like us to include that into the report?
Which one?
The concrete report, like about the humidity and you know, how the concrete is cured.
Well, I would like to read what you learned from this lecture, and basically the report should include everything is being taught in this section, concrete section. Also, look at this way. If we don't include it, I'm not going to take points off just because you didn't mention the humidity and the temperature on the theory sections, or you didn't mention on the discussion. There are certain things that I ask, like modulus of elasticity, etc. But these things are up to you. I'd like to see, I'll give you extra points if you mention the humidity and the temperature, effects of humidity and temperature on the concrete overall strength, and how it is being, like how the temperature and humidity is kept at a certain level on the outside environment on the construction side. That will be plus for your report, and you can keep the report for future references. So you can go back and read your concrete report. If you are working on construction side, if you ever get a job on the construction side, you can see why actually they are applying the curing compounds, or why they are performing slump tests, or why they are taking concrete samples from the construction site during the construction. So it's up to you. If you add these information, you can get extra points. If you don't, you're not going to lose points. But you should have the requirements on that's given to you on the previous lectures, what you should have in the Concord report. And the sample report makes it clear. I think I close the sample report. You can even see the points that you can even see the sections that I took points off from this report, sample concrete report. Over here, so excellent. So let's look at this. The concrete compression test is used to determine the compressive strength of concrete at certain curing points, curing conditions within 28-day mark. Perfect. Mention the curing conditions, temperature, humidity, not in details, but I assume that he already knows the temperature and humidity, how it affects the concrete compressive strength. Correct? This is the one point that he made. Austin, right?
Yes, sir. Yes, sir.
Okay. And the second, it is expected for concrete to continue to cure past 28 days, but by 28 days, it will have reached high enough compressive strength. This is again general information, which I ask for general information. I don't want I don't want to see too many numbers over here. That makes sense to me, but it's not going to make sense to you in the future. But if you give general information, that's even better, because this is your own words that I know. It's not copy and paste from internet. Okay. He's mentioning that it past 28 days, concrete still cures. And I mentioned that in previous lectures that Hoover Dam still is curing, even though it's been years. But it states that 28 days is the maximum that we can reach, the number that we can reach at 28 days. That will be the baseline for your design. The resultant data will produce the stress strain diagram, which is similar to aluminum's stress strain diagram. Exactly, this is what I say. So he basically summarized what I explained in the lecture. This is due to the hardened concretes being very brittle or extremely hard. I mentioned that aluminum is much more brittle compared to steel. Steel is more ductile, it can stretch, but aluminum is brittle. It just breaks without deforming as much as the steel does. This is basically the explanation of the data table 28 days and 7 days data. What is the 70%? 70% of the maximum strength is reached at 7 days, and the maximum strength after 28 days of curing was found to be this number. And some facts, and it mentioned that this tells me that these students compared the data points or the results from this test with the Quikrete specifications. Again, the information about maximum compressive strength for the 7 days. And these are the this section, this paragraph, last paragraph is, I believe, it's for the errors in this lab. The factors that could affect the overall hardness of the concrete is the water cement mixtures and the external environment, which means that we didn't have during that this report, I believe 2018 or 17, our curing humidity chamber was not working. We kept the sample in the mechanics of materials lab under the sink. We were giving water. When we see that water is not present on the concrete sample, which shouldn't be the case, you should keep it at the certain humidity, 80 to 85%. If we don't, you get horrible result, not the one that you expect. Even if you reach the, let's say, more than 4,000 psi compressive strength, you might have shrinkage on your concrete. You might see cracks on your concrete, and cracks are the biggest problem in the concrete. Basically, again, comparison between Quikrete and the numbers that we calculate. And you should also mention the modulus of elasticity comparison, why they are different, or what you get for the Young's modulus numbers. I believe this answered your questions, Austin.
Yes, sir, you sure did. Thank you so much.
No problem. Let's go back to shrinkage. The curing compound, I mentioned that, humidity. What happens if we don't keep the perfect conditions, or if we don't use the curing compounds? You will see shrinkage. What do you understand when I say shrinkage? Let's ask this question to Karina Griganas. Karina?
Hi.
Let me ask you a question one more time. What do you understand when I say shrinkage on concrete? How concrete can be shrinking? It's strong, powerful.
My assumption is when the concrete starts cracking is due to the shrinkage.
What do you need for shrinkage? To shrink something, you
Oh, too much heat?
Too much heat, expansion, yes, that's correct. And there should be some tension involved for shrinkage, right? Because if something is shrinking, right, it is being pulled, right? Let's
Yes.
say, get an object, or if you have the eraser in front of you, try it on the eraser. You're gonna be pushing on the sides, and that will be opposite and exact forces. That's responding the compression force. But in concrete, with the heat or with the other environmental effects, what happens? Concrete starts shrinking, and the tensile forces develop inside the concrete. When it shrinks, you will see the cracks in the concrete. And more than likely, the concrete that you are looking at, let's say if it's a column, girder, or even the concrete pavement on New Orleans roads, you see the concrete pavement has 8-inch thickness, and it has the rebars. The rebars are made of steel. What happens when water and steel reacts when they get together? Overnight, you see the deformation, rusting on the steel that kills your steel member inside your concrete, and that's caused by shrinkage. So one thing triggers another thing, and at the end of the cycle, you get weak concrete member or concrete pavement, concrete column, whatever you name it, due to shrinkage and cracking. So your point was right, that cracks and but reduces the overall strength of your concrete with the time. You might get this strength, 28-day strength, 4,500 in the 28 days. But with the time, if you have shrinkage, cracking in your concrete, that number is going to go down with the time, over time. Did we understand the shrinkage now better?
Yes.
Okay, let's look at the example. This is the shrinkage on the concrete. You see the rebars? From this crack, water can get into the concrete, and that water is gonna start chemical reaction with the steel. It will get rusted, and then you screw. Look at this. Creep is different thing. I'm not gonna get into details, but if you're a civil engineer, you should know what the creep is too.
Is there a way around all that?
Well, maintenance is the key. It's like you buying a car. When you buy a car, if you take it to maintenance regularly, you shouldn't have problem. But if you don't maintain, then you will have to pay the price sooner than later. Does that make sense? The entire infrastructure in the United States is, I think it's below C+, really low. Like the assessment report recently, I think it was in 2020, everything is falling apart just because of the low maintenance and low inspection. If you inspect it regularly, you can always rehabilitate the existing members. Because if you know that where the problem is, based on the inspection reports, for example, the one that we were looking at earlier, okay. I show you guys the bridge example. You can see it now. But if you do regular inspection on the bridge, there was, I just showed it to you, but that's coming anyway. Then you can rehabilitate that section. You can use, for example, carbon fiber rehabilitation on concrete columns that add additional strength to your concrete member. That's being used in California because California is the earthquake seismic zone, in the seismic zone. When I was working on my thesis a couple of years ago, my master thesis, I was looking into rehabilitation methods for structures on or around the seismic zone, especially in California. They use carbon fiber and they wrap the concrete columns that is weak and that needs to be rehabilitated. And the concrete fiber, carbon fiber, it adds additional strength to your column or to your beam. So there are ways to postpone and prevent the failure, and it's the maintenance and getting samples from your structures. I don't know if you guys ever seen or if you have heard, you can even take core samples, cylinder core samples, like we tested our concrete cylinders. You can take the sample from the existing structures, from concrete column or concrete girder, and you can take it to the lab and you can see what is the compressive strength of your member during the service conditions. Is there any change? If so, what is the change? Or how you can prevent the failure, or how you can predict the failure. So these are the ways to go around it. But the cracking is like a cancer, to be honest. Because once the cracks are opening, then the rusting starts on the steel members, and you can't stop there. Okay, any question about the concrete again? About shrinkage? There is one question. Okay, somebody is leaving, that's fine. We're done with this. Okay. Let's go to question 4. What are the factors that will affect the concrete compressive strengths? We already discussed this in the previous conversations. Really quick. I'm going to get this answer from John. John. There's only one John, right? John Guidry. I think he's not here.
Hey, I'm sorry, it's April. He just texted and said that he told you that he wasn't feeling good. He got his second.
Oh, yeah. Yes, it was him, right? Okay. Okay, then let's go with. Let's go with. I don't know how to spell your pronounce your name, Juan Valadares.
Oh yeah, it's Vaughn.
How do you pronounce your name?
Vaughn.
So,
It's pronounced Vaughn.
Juan, I'm sorry, Juan. Okay.
Yeah, no worries. Sorry, what number is this?
So we're looking at the question number 4. What are the factors that will affect the concrete compressive strength, which we discussed in a few minutes ago?
Just like the quality of ingredients, the ratios used, cure time, temperature, internal air.
Perfect. That's enough. Thank you so much.
Yeah.
And then number 5, what are the characteristics of concrete that can be changed with the addition of admixture to the concrete mix? I just pulled up the website and there were some characteristics that we were looking at. And this was, let's ask this question to Tyler Frick. Tyler? I think he's not here. Alexander Luich. Alexander?
Yes, sir. I'm here. What was the question again? We're looking at 5, right?
Let's see your face. Do you have the camera? I
Yeah, I
forgot.
have a camera.
Some of you guys, I haven't seen you guys, so I forgot the faces.
Yeah, I have a camera. I'm in the lab upstairs.
Oh, got you. Okay.
Yeah.
So let's look at the question. What are the characteristics of concrete that can be changed with the addition of admixtures to the concrete mix?
With addition of admixtures, the characteristics can be changed when you want to prolong the mixing period, if you have to go to a further job site, or if you want it to cure faster, you can spray chemicals on top of it when it's curing, and you can also water it after you. Those are some admixtures that you can.
Okay, that's pretty much the answer in general. But real and the perfectly structured answer can be found on this PDF. But you're good. Thank you, Alex.
Actually, I have a question about
No problem.
the admixtures. So I remember in the beginning of the class, I asked you a question about timing with the concrete curing, and you said something about sugar. Sugar could slow.
Yes.
Do they actually do that?
Yes, they do that. That was an example, a strange example that I was reading on one of the articles on construction blog. That was the incident was in New York. Imagine you're in New York, and I'm not from New York, but I see from the movies the traffic is heavy, congested in New York, and you're trying to get from one point to another point, and you have only 90 minutes. In New Orleans, that's normal. You can get from point A to point B, from West Bank to East Bank in 90 minutes. But what can you do if you're in New York or New Jersey? If you're in traffic, and you can use sugar. That guy was using sugar, and he was always keeping a sack of sugar in his concrete truck for those incidences. And it's true. And I believe this handout includes the sugar somewhere. Let's see. There you go. Retarding admixtures are used to slow the setting of concrete and to retard the temperature increases. So retard means it just changes the setting time of the concrete by slowing, actually, slow the setting of the concrete. So it doesn't set when it is on the concrete track. Concrete track, the concrete is always rotating in that track. And in order to slow the setting of the concrete and change the temperature to lower it, you can use various type of acids or sugar derivatives. So the products made out of sugar. Some concrete truck drivers keep sacks of sugar on hand to throw into concrete in case they get caught in traffic jams or otherwise delayed. Retardant admixtures are particularly useful for large pools where significant temperature increases may occur. They also prolong the plasticity of concrete, enabling better blending or bonding of successive pools. Retardants can also slow the hydration of cement on exposed concrete surfaces or form surfaces to produce attractive exposed aggregate finishes. So I believe this answered your question.
It did. It did. Thank you.
No problem. No problem. So
Actually, that is very interesting.
it is. It was interesting to me
Yeah.
when I heard it.
Mm-hmm.
Yeah. There's always one old school solution. You know, instead of using chemicals, you can use sugar.
That is cool.
Okay, let's go to number 6. Calculate. I'm not gonna go and do this problem, but I will answer questions if you guys have any questions. Calculate the stress and strain values for the data points given below. Draw stress versus strain diagram with the calculated stress strain values. Determine the yield strength, Young's modulus, ultimate tensile strength, and fracture strength. Pretty much. I'm trying to pull up that part for exactly this. Same calculation that you have performed over here. If you follow the same procedure, get the graph. Once you get the graph, the ultimate tensile strength, you should circle it and highlight it or whatever. And the fracture strength and the yield point. In this problem, it was always the yield point. I don't know that I don't have a solution right now, but do you guys have any question with this? Awesome. Did you have a problem with that?
I actually didn't get to finish that part. I spent too much time on the other parts. I do understand how to do it.
Okay, good. Good, perfect. So this was the same problem that I saw in the review session. I will get to this, but I have to take 5 minutes break. I have to check on the baby, and I'll be back in 5 minutes. We have 30 more minutes. I will extend this session. I'll record after 6:30 and continue if I need to continue. And you can leave if you need to leave at 6:30, and you can watch the remaining portion on Moodle on YouTube. So if you have to take a break for 5 minutes, you can take a break, and I'll be right back. Okay?
Thank you. Thank you, sir.
No problem.
Can y'all see y'all's grade on Moodle?
Are they posted?
I think he said they were posted, but I can't see my
All right.
grade.
I haven't checked. I'll check right now.
Hey, y'all, the grade is posted on WebStar. It's just the midterm grade.
All right, thanks. I'll check WebStar.
No problem.
Alright. All right. Now, can you guys hear me? I'm back.
Yes, we can.
Okay, yeah, that's perfect. So in the meantime, did you guys look at the problem? Number 7? I assume yes. So let's go with Rami. Rami Musin. Musin. Okay,
Yes.
how would you approach this problem? Step by step. Don't be shy. Continue, and I will help you. And let's get through this problem. I'm not gonna solve it, but I will explain the steps.
All right.
Take your time. So you have a concrete column, F prime C 4000 PSI. This was PSI. Okay. So if you use KSI, that's fine, but just the calculation. But F prime C is 4000 PSI. And this column is built into the ground. And it has the length of 5 feet. So the length is 5 feet. Correct?
Yeah.
Let's continue. The dimension of the cross section B is the base is 2 inch and D depth is 4 inch. First, you need to calculate the maximum load that results in compression failure in the concrete column. What is the equation that you need to use, or how we can?
It's P over, it's force over area.
Perfect. So the equation that we were going to use was stress P over A. P is the load.
And the numbers are 2,000 for the load and 8 for the area.
Perfect. So load was what you got for the load? You're saying?
The P max was 16,000 pounds.
And how did you get this number? You have the stress, you multiply the stress with the area. And the P should be 16,000 based on Musan's calculation, but I didn't do the calculation. Double check the number later on. And then let's go to B. Calculate the modulus of elasticity of the concrete based on the given compressive strength 4000 psi. And in this way, in this case, you only have one equation that you can use because you don't have the stress strain graph. And the equation, we just covered the equation in the Excel spreadsheet. I'm not going to ask you what exactly equation, but it's the ACI equation, 57,000 square root of F prime C
So it's F prime of C was, I got 4,000 for F prime of C.
If you use this equation, then that should be correct. So
And
Yes.
then the fine, or would you try to say the answer?
let's see. Let's see. What was the 4,000, right? It was 3,605. Is that what you got?
Yeah, I got that.
Okay. If you got that number, then that's correct.
Was it okay to put it in PSI instead of KSI?
Yeah, that's fine, as long as you got the correct units. So if it was on, what did I calculate? I calculated in the KSI. If you don't divide by 1,000, then you get on PSI. But if you don't specify the unit, that's a big problem. Not even in the exam, because it makes a huge difference. KSI and PSI is huge difference. So let's go to C. Calculate the change in length of the concrete column when it's subjected to P 8,000 pounds. What about this?
I did the change in length over the length. And I got 8,000 over 8. So 1,000 PSI.
Strain is equal to deformation over the gauge length. And again, that is deformation. We don't know the deformation, but we know the strain, right? So we're solving for deformation. What is the strain? We don't know the strain, but we can get the strain. Strain times length. So you get the strain from E. E equals stress or strain. So at 8,000 pounds, let's see what is the corresponding stress. Compressive strain or compression stress. Area, what was the area? 8. That's 1,000 PSI, correct?
Yes.
Is that correct? Perfect. So the only reason I put 8,000 because I wanted to stay in the elastic region to make the question problem statement correct. Because if that number 1,000 PSI was 3,000 or 4,000, I can't use that number to calculate the strain because this equation is only applicable on the elastic region, correct? That was a small detail. correct? So f prime c over 2 is here 4,000 divided by 2, which is equal to 2,000, which is bigger than, correct? So I checked, I'm in the safe elastic region, and I can use the equation. All right, so I got 1,000 psi. Now let's solve for the strain. Is equal to stress divided by Young's modulus. And what is stress? 1,000 psi. What is the Young's modulus? Young's modulus is
I got a decimal. I got 0 or 0.00272. Oh wait, no, my bad.
let's
I got
see.
for the Young modulus 360
Yeah, that's what I got.
4976.
So this is gonna give me the strain. So 1,000 divided by this number. Let's view the spreadsheet. This is the strain that I got. Right. Let's copy this. Correct. So this is what I got. Then, since I know the strain, I'm gonna bring this over here. I'm gonna replace this with 5 because this L is 5, correct?
Yeah.
Don't forget to multiply by 12, so you get in inches. So 0.0277. Five feet multiplied by 12 inches. 0.01664 inches. If you don't multiply by 12, if you don't convert to inches, I'm not gonna take points off. As long as you change it from inch to feet. Any question on this? Musa, Robin?
You got me at the end with the conversion. I didn't do the conversion.
That's all right. As long as you got the calculation right, doesn't matter it's in feet or inches or meter or centimeters, as long as that's correct. Okay, so this was the answer.
I have one question. Do you care about significant figures? Because I only got 0.016. I just put that. That's good.
That's enough.
Cool.
For me. But usually you keep if you're working in the lab, you should keep at least 4 significant figures. If you're working on the spreadsheet, you don't have to keep track of the significant figures because this equation is based on the strain number over here, and it keeps the decimals from this cell. But if you're doing manual calculation, then the problem starts, because if you cut this number at 3 decimal 0.016, and then you keep the continue your calculation, your final number is going to be off, because you don't consider the other significant the decimals. So
Okay, I will keep that in mind.
yeah,
thank you.
for this exam, I don't mind. But if you're working at the lab, or if you are working on your design after you graduate, get a job, then you should keep at this 4 significant figures when you're doing your calculation. And at the end, you can round up your numbers after you finish your calculations. But till you calculate and complete your calculations, you have to take into account this at least 4 significant figures. We should include them all, to be honest, just to be on the safe side. Make sense?
Yes, yes.
Okay,
Thank you.
perfect, no problem. Mm. One second. Just right there. So we answered this problem too. That's good. This one, the pipe has an outer diameter of 40 millimeter and the inner diameter of 37 millimeter. It's a hollow shaft. And I saw a similar problem in class, and I posted a video on YouTube before that video was already on my channel. And you can find the solution for this exam, for this problem on the video. But before I show that link, I don't know if you guys seen that video before, but I'm gonna ask someone about how to approach in this problem. Who's left? Alexander, Jens, Austin.
I could do it.
Austin, go ahead. Yeah.
First, you would have to find the polar moment of inertia.
Mm-hmm. Mm-hmm.
That would be pi over 32 times.
I'm not gonna solve this problem like the previous
okay.
one, because this one has already solution on YouTube. Calculate the polar moment of inertia, right? Okay, and then
Then to find the maximum shear stress, you would just multiply the torque times the radius all over the polar moment of inertia.
that's correct. But there are things that you need to take into account until you get to this stage from, okay, you calculate the polar moment of inertia, this is 1. So let's say this is A, and this is D, and you have B and C. First, when you calculate the polar moment of inertia, you have that number. You know that you're going to use that number for the calculation of maximum shear stress, TC over J. And we
And
know
it's the
C,
outer radius, right?
yes, C since the question statement is asking for the maximum shear stress, that C is going to be the outer radius, right? That's the radius. Because we know that we can also calculate the shear stress that is that's between the neutral axis of the shaft, between neutral axis of the shaft and the outer surface of the shaft. We know the minimum shear stress, which is 0, is in the middle neutral axis. There is no shear stress in the middle, because in the middle, let's say you have this circle, insert, and this. Okay, this is your circle, right? And in the middle, let's say this is your diameter. And this is your neutral axis at the same time. And at center, what is your radius? What is this? What is the C at the center? Let's say the diameter is for this sample 2 inches. Radius is 1 inches. According to this equation, what is C in the center at the neutral axis? 0, correct?
Yes, sir.
In the
Yeah.
middle, it's 0. So if I use T times 0 divided by J, it will be 0. And I can prove that there is no shear stress developed along the neutral axis. That's 0. And I mentioned that in class that if you get the you go home and try to get the spaghettis and try to rotate it, apply torque on one side, you will see that the spaghettis along the surface is deforming first because maximum shear stress is developed at the outer surface and maximum shear strain is developed on the other surface as opposed to inner surface. Inner portion is 0 at the neutral axis and it's experiencing less stress and it goes through less deformation until failure. So if I'm looking for the maximum shear stress, then this C is going to be 1 inches. I can also calculate the shear stress at 0.5 inches from the neutral axis. That would be half of the maximum shear stress, correct? That's why I can say this design hollow shaft is perfect for the against torsion because you are saving from the material. You're taking the middle portion out, which you don't need it. Do you need the middle portion if you're using under torque? If the service condition is only experiencing torque or torsion? No. Your goal is to eliminate the reduce the maximum shear stress applied to this specimen and resist the shear stress forces. So over here at the stage B, after giving this background, first you need to sum the torque. You're gonna sum the torque, applied torque. You have 80 Newton, 20 Newton meter, and 30 Newton meters. One is going clockwise, the other one is going counterclockwise, and then the other one is going clockwise. So you're gonna start with clockwise or counterclockwise. You will assume one or another is negative. If the counterclockwise is negative and the clockwise is positive, and you'll say, let's say, I'm assuming so 90 Newton meter. That's what I did. Go back to check my video and check it out again. So this is your overall applied torque to your circle shaft. So this is going to replace your torque number, and you can use that number to calculate the maximum shear stress.
Would that be considered the sum of the moment? The torque?
What is it?
When you're adding the torques together, wouldn't that be the summation of the moment? of the
I think
torque?
so. Yeah, I think so.
Okay. Wait a second. So you're saying that summation of the moments, that's exactly what it is. Torque is the moment, right?
Yes, okay. I just wanted to clarify.
It's the same thing. Torque is Newton, which is the force, applied force, times the distance, meter, correct? And what is the moment? Force multiplied by the distance, correct?
Yes, sir.
Okay. For example, let's make it clear. This is the beam bending that I was going to cover today, but I'm going to left over to next week. But this is the moment that we're dealing with, maximum moment maximum and maximum stress that are related. To calculate the maximum moment, what I do here, are you guys able to see the screen, the spreadsheet?
Yes, sir.
Okay. So I'm trying to calculate the maximum moment over here. And to calculate the maximum moment, I can look at the equation that says force multiplied by the distance A. So whatever is this distance over here, A, I have to multiply by F, applied force over here. That's gonna give me the maximum moment. But in general, moment is force times distance, and torque is force times distance. That's the same thing. And what it does when you apply force at this point to this beam is trying to rotate clockwise, correct? If you apply load on this beam, that beam tries to rotate, correct? Okay, let's make it one more time. Okay. That's the beam. Are you guys able to see my screen? I mean, my video camera?
Yes, sir.
Yes.
Okay, that's the beam. And I'm applying a force on top. It's trying to rotate clockwise, correct? That's what it is. It's rotating clockwise. It's the same beam over here. Imagine this beam is cut from the center, and the only support is one end on the left side, pin support. And I'm applying force with my finger. It is trying to rotate clockwise. And there is also internal opposite and exact forces and exact moment that is resistant to external force. Correct? Otherwise,
Yes,
this
sir.
beam will keep rotating. That's the whole point. Torque and the moment is the same thing. It's just the orientation is different when it comes to beam and the circular shaft. And you still over here, the force is applied in this direction. Let's make it more clear. This is torque applied this way, and this is your center, and this is your radius, right? Force applied this way, perpendicular to neutral axis, and your moment arm, your distance to neutral axis is R. To calculate the torque, I have to multiply, I'm sorry, this is the force, my bad. Force times distance. Force is applied at a distance to neutral axis, and that gives you the torque, applied torque. And it's the same case on the beam. Force is applied at a distance to the support, and the moment is calculated by using force and the distance. Same. Any question mark on this?
Would you be able to use the right-hand rule for that problem? In other words, to determine the way the inertia is going?
Yep, yes, you can.
Okay, thank you.
Mhm. Next time when you use a screwdriver, try to use the right hand rule. This way you're gonna see which way the screw is gonna go in, clockwise, counterclockwise. That's when you can use and you can prove the right hand rule. So first you get the applied torque overall after you summing clockwise and counterclockwise. Then what else do we need? And I believe that's it, huh? Once you get 90 Newton meter torque, you replace it. 90. In this problem, you're gonna use the diameter 37 and 40 in the polynomial of Fibonacci will be included, and the overall outer diameter. This is gonna govern. This is the gonna replace the C actually 40 millimeter. And whatever is the number for J, you will enter it here, and it will give you the maximum shear stress. Let's see. I will take a look into one more thing. In the meantime, if you have question, ask me. I don't think there is question.
I have a question about viewing the grades because when I go on Turnitin, I don't see a grade. But one student said he found it on Webstar, so maybe I just don't know how to use Webstar. I can't find the grade.
Okay, I will show you how to get the Webstar. One second. Torsion example. There you go. I've been left with 6 minutes. Exactly. This is in detail the explanation. Next, we're going to look at our equation, since we are looking at the distance from the neutral radius. And this is outer radius, this is inner radius. So polynomial Fibonacci equation is given at the end. Pi over 2, the outer radius minus the inner radius, just to take into account the missing portion in the middle. And then you get the 90 meter really quick without going through these sketches. And if you get used to calculations, and it shouldn't take more than 2 minutes to calculate the maximum shear stress developed in this pipe. So that was the answer for the problem number 8. For Webstar, let's look at the Webstar.
So, question, it's not 40, it should be 0.002 meters.
Correct. That's a diameter. This one is the diameter. My bad. Yes, we're gonna use radius.
Okay.
I did it correctly over here, but I didn't pay attention to today's diameter over here. So that will be 20 millimeter or 40 millimeters divided by 2. Thank you. Well, Rami, if we go to UNO Webstar and check your grades, have you done that before? Do you see any other grades that is given to you on different classes? Or is
no, this is my first semester at UNO.
No, did you receive the midterm grades on the other classes?
No, I haven't checked on. I just looked at them through Moodle.
Oh, no, no, you're gonna go on website and go on website and see your grade. Okay.
So it's under the Student Center in WebStar?
Yes, Student Center, you will select from the drop-down menu, you're gonna go to grades. When you go to grades, you will select the midterm grades. And you should see your grades.
All right, thank you.
Mhm. Okay, so I will quickly go over the beam bending. And I will see that the actual test last year I did and I videotaped it. See if I can find it. There you go. This is a short video that's in our lab. I actually run this test. Are you guys able to see the screen?
Yes.
Okay, what you see here, you see the aluminum beam. That's one aluminum beam. And you see 1, 2, 3, and 4 gauges. And you have one more gauge over here in this strain gauge box. So this box is attached to this aluminum. This aluminum, give me 1 second, guys. One second. Go ahead. Okay, so I was mentioning the gauges. You have 1, 2, and 3. Third one is in the middle. That measures the maximum deformation, maximum deflection on the beam. And the gauge on the left side, on the left end, that is measuring the deflection from the left end, and it's a 4-inch distance from the left end. And the other one on the right side is the 6-inch from the right end support. So we measure the deflection at 3 points. Sorry, I wasn't sharing the screen. My bad. My bad. Now, are you guys able to see the screen and hear me?
Yes, sir.
Sorry, the baby needed to have water. We just have 4 months of baby. That's why tough times. Okay. So let me
Congratulations.
explain. Thank you. Thank you, Austin. Let me recap these gauges and explain to you guys why we are measuring the deflection at those points. Before that, let's go this old handout. This is the old but gold handout. It's been used since I was a student. Okay, this is for beam bending, and this is the sketch for the aluminum beam. This shows you the dimensions of the beam, locations where we measure the deflection. So overall length for this beam is 18 inches. It's the same exact beam, 18 inches. And the load is applied at 2 different locations that are symmetric to each that are symmetric. So 7.5 P over 2. The 7.5 is the distance from the left support to the point where the load is applied. So this is your left support, and this is the first loading point right here. Are you guys able to see my mouse?
Yes, sir.
My mouse cursor? Okay. So this is the first loading point, and this is the hydraulic pump. So let's run this test a little bit so you see. So I Start testing. Set up the hydraulic gauge. And as I apply pressure with the hydraulic gauge and I stop the gauge because oil is leaking. This is the most accurate test, by the way, that we perform every semester. And we get the perfect results with really good accuracy. Anyway, the first loading case is the 150 pounds. And when I apply the force, these two loading points, it is trying to pull the beam down. So let's see this. Stop share. Okay, do you see my camera right now? Okay, this is your beam, and it's supported at both ends, left and right. And then I have two loading points, 1 and 2. As I apply pressure with the hydraulic pressure machine, these 2 points is applying pressure. I'm sorry, stress, force at these 2 locations. One loading point is 7.5 inch away from the left end, and the other loading point is also 7.5 inch away from the right end. So the distance from right end to the loading point is 7.5, and it's the same way for the other loading point, and it's symmetric. And you will see how it's going to be helpful to have the symmetric beam on your calculations. You can save some time here. You also see the distance between the center of beam and the loading point, 1. That's called P/2. The first one is A, the other one is B. A and B are the loading points. And the CL is the center line. This is 18 inch. So if you cut this beam in half, you have 9 inch on the left side, you have 9 inch on the other side. So our goal is to measure the deformation at delta 6 here, 6 inch away from the left end, and delta 9, which is in the middle, center of the beam. We want to see how much this beam will deflect if we apply that force. You see this beam is deflecting, and I want to see how much it will deflect in inches. Also, we want to see the deflection at delta 4. I mean, at 4 inches. Delta is the deflection. And this 6 inches showing the distance from the left hand, at 4 inches showing the distance from the right hand. And this one is pointing at the strain gauge. So assuming this is the beam, you have the strain gauge here that is measuring the axial deformation. So you have the strain gauge over here, and this beam is deforming, deflecting. You can see, if you look in closely with the microscope, the bottom portion of the beam will be under tension, and the top portion will be under compression. So you measure the deformation with the strain gauge, which will give you the deflection. And you also measure the strain gauge. You measure the strain with the strain gauge that will be used to calculate the modulus of elasticity. This E value over here. You also see the cross section over here. I mentioned this cross section. We cut the cross section from this beam. Imagine I cut this beam and I look at the cross section of this beam. I have the base is 0.5 inches, and I have the height 1.25 inches. And this is gonna give me the moment of inertia by using the moment of inertia calculation. B h cube over 12, B is 0.5 base times height cube over 12. I saw a couple of examples. I worked out some problems with the moment of inertia before. That C is the 0.625, that is the half of 1.35. You will use the C to calculate the maximum stress. Again, let's see is the distance from neutral axis to the top fiber to the outer surface of the beam. And if you're trying to calculate the maximum stress, what I said for the torsion is the same way. Maximum stress is developed at the outer surface. You have zero stress development at the neutral axis. You have zero deformation at the neutral axis. If you go, as you go further away from the neutral axis, you start seeing more stress developments and you start seeing more strain developments on your member B. Are we okay so far?
Yes, sir.
Okay, good. So 1, 2, 3 equations. We are familiar with the moment of inertia. We haven't seen this equation before, but you can relate this equation with the torsion equation, Tc over J. So T is torque is replaced by a moment. That answers your question again, Austin. You were asking about the torque and moment. We can use the torque with moment. Yes. Same.
Yes, sir.
And C, again, that's the C from the torsion. I don't have the example up, but you can pull up the torsion equation, Tc over J. And J, polar moment of inertia, is replaced with I, moment of inertia. Okay. And you have one more equation, modulus of elasticity, stress over strain. And again, this is only applicable on the elastic region. So if you calculate the stress in the elastic region, if you calculate the strain in the elastic region, you can calculate the modulus of elasticity. In this case, in this example, in this test, strain gauge, that device right here, that's going to give you the strain. And you will calculate the modulus of elasticity by knowing calculating the stress in the earlier steps. This is a long process. I'm just going to go over it, and I have the sample problem that I will post, and I'm going to go step by step and solve this problem in our next meeting. Basically, what we are trying to prove is once you run this test, once you complete this test, you will have deflection at 4 inch. You will have the deflection value at the middle, maximum deflection. And you will have the deflection value, measured value at 6 inch, right? 6 inch, 4 inch, and middle. And you will compare these numbers with the numbers that you are going to calculate using the conjugate beam method. So there are several ways to calculate deflection. There are numerical methods, conjugate beam methods, and several others. This is by far the easiest one, conjugate beam method, but you will see how long it will take for you to calculate the deflection only on one beam at 3 locations. And imagine the size of the project that you're going to be working. If you're a structural engineer, you're going to have hundreds of beams on even 5-story structure if you're designing a steel structure. How are you going to solve the deflection for how we're gonna solve for deflections for every single individual beam to meet the criteria. That takes time. Either you're gonna use spreadsheet that's gonna give you the deflection at certain locations. Usually the maximum deflection governs. You want your maximum deflection to be less than whatever is prescribed by the American Society of Civil Engineers. So only variables that you can change is the applied load, and you can change the length of your beam. You can change the orientation of beam to calculate deflection or to reduce the deflection. What parameters can be adjusted? That will be your job. You will change the depth of the beam. You will change the length of the beam, this base and height. You will see if I change the base, how numbers are changing. Let's say base is 2 inches and the height is jumping from 2 to, let's say, I'll make it 8. Look at the deflection at 10, how it will change. 0.01. Deflection is reduced, right? Compared to 0.0081. If I make the base, if I keep the base at 2 and if I increase it to 10, let's make it 4, 5, 1. Deflection is almost gone. Let's format. This is where the significant figures comes to play. I want to see more decimal plays. You see, I just increased the height from 4 inch to 20 inches. You see deflection is increasing. So by playing with the base and height, which is the cross-sectional properties of your beam, you can increase or decrease your deflection. That's our goal. And why actually we are running these tests, I will show you the example right now. Okay, there are maximum deflection limits when you're designing your beam. It can be cantilever beam or fixed beam or simple supported beam, depending on your design. This is for American Wood Council, but you can look at the steel section. It's L over 360. You will see it all the time. L is your span length. Span length is, in our case, is 18 inches, correct? This is your span, overall span on your beam. L over 360. So your maximum deflection should not be greater than L over 360. It should be less than L over 360. If it's more than L over 360, what can you do? How you can lower that number? Let's ask this question to Patrick Bouquet. Patrick?
Yes, sir.
I'm asking
Can
you
you
one
repeat the
simple
question?
question. Yes, I can hear you. I'm asking you one simple question. Let's say you're designing this beam, okay? It's a floor joist. And this floor joist has 10 feet length. This is your limit, L over 360. This is your maximum allowed deflection. Maximum allowable deflection. So the specs tells you if your span length is 10 feet, why this is not picking up? I'm trying to select the 10, but it's not giving me that option. There you go. There you go. This is 10 feet, but I'm going to use inches because I have to use inches. Deflection is not going to be in feet. So that 10 feet is going to be 10 times 100, 10 times 12. That's going to be 120 inches. Then I'm going to use this number. There you go. So ASC, basically, it's forcing you to get your deflection less than 0.33 inches for your beam. This is your beam. Imagine this is simply supported beam. You have supports at the end. And your goal is to lower that allowable, your deflection based on the given load, whatever the load is applied to your beam. Your job is to lower that number smaller than 0.33. And the ways that you can lower that number is changing height and base. That will increase or decrease your moment of inertia. So if you increase the depth, so this is your depth, let's say 1 inch. And if I increase that to 2 inches, let's say originally my base is 0.2 and my height or depth same way, it was 1. I found the deflection is 0.65. Copy that right here. And then from 1 inch, I went to 2 inch. I increased the depth. Let's look at this number now. See which one is bigger. Obviously, this is bigger than this. So I lower my deflection by just changing the depth of my member, right? Correct, Patrick?
Yes.
Okay. So I can also check quickly if I know the span length, if I know the span length of my beam that I'm designing, say 10 feet, and if I know what the spec says, the ASCE, American Society of Civil Engineers, I can use that equation to calculate my limit, know my limit. And if I know my limit, and I know I should be less than this number, then you change the orientation of your beam, or you change the loading points, There are many ways to load your beam or design your floor, joist, etc. So my question was to you, how you can reduce your overall deflection or maximum deflection on the beam you're designing. And I give you the answer. The answer is to change the moment of inertia, increase the moment of inertia to lower the deflection. And to increase the moment of inertia, you have to increase the depth of your beam, make it thicker and deeper. That's the
Makes sense.
okay. So our goal in this experiment to prove that the equation conjugate beam method, and these equations are derived by the conjugate beam method, by the way. So we will also prove these equations from the conjugate beam method, and we will see that in how these equations are accurate in our calculations compared to the actual result from the experiment. Because every year when I do the calculations, numbers are super close. So whatever deflection I get here at 4 inch, I compare that number with the number that I calculated using the conjugate beam, and it's quite to be close. So the conjugate beam method is working perfectly. And same way, I check the deflection here at 9 inches, and I compare that number with the result from the calculations. And then I get the deflection here at the 6 inches from right hand, and I do the same thing. So your job will be cross-checking the results from the test with the results from your calculation. Is there any question so far in this overall looking at the big picture? All you have to do, compare the results from the test with the results, deflection results from your calculations using the conjugate beam method. And we'll get the conjugate beam method next week. So far, any question?
No, sir, you made it pretty clear. Thank you.
Okay.
Yep.
You're welcome. So also essential information in the regarding the background of the moment of inertia and the deflection calculations will be given, it will be on the model. Okay, so you shouldn't have any problem with the background, but I will also, time to time I give the background and the details as we go. So these are you're gonna have 2 different tables, but this semester I will keep it short. We do 2 different runs just to get the average of 2 runs. First run is starting with the 150 pounds load, applied load. So in this video, this one is the 150 pound load applied, 75 on 1 point right here, and 75 on 1 loading point. And then I measure the deflection. I'm taking the measurements. And then I'm taking the measurement in the middle from the center of the beam, which will be the maximum deflection. And then I take it over here as well. And then I go back to 0 and 0 the gauges. And also I take the strain gauge measurements on each run. Right there. So delta 9, I got my measurements. Delta 6, deflection at 6, I take the measurements. And delta 4, deflection at 4, I take my measurements. And I also take my strain gauge measurements from that small device right here on the side. This device, it tells me what the strain is, and it tells me the strain in micro. It tells me the micro strain actually, and then I convert that to strain. And I will give you the conversion unit next week. So once I finish the 150, I go to 300 pounds. So I add extra 150 pounds and I get to take the measurements, same measurement. In the middle, 9-inch, 6-inch, and 4-inch. And I go to 450, take the same measurements. And then usually we do 2 rounds and then we take the average of 2 to be more accurate. So once you get these measurements are going to be given to you, by the way, because I already have the data. And you will compare this deflection at 9-inch with the deflection you will calculate using the conjugate beam method. This is the overall steps for the conjugate beam method. You start with the free body diagram. This is for 450 pound loading case. 450 divided by 2 is 225. You will have the equal and opposite forces at the support. 225 at the left and right hand support. And then you will calculate your shear diagram. You will draw your shear diagram. You will draw your moment diagram. These are the basics that you should know already. And the tricky part starts here with the conjugate beam diagram. You will have to read the conjugate beam method before you draw the conjugate beam diagram. And we're gonna get there next week. So for now, stay safe and healthy, and I will see you guys next week. Also, in the meantime, please take a look at the beam bending lab guidelines. It gives you step-by-step explanation how to develop your report, especially your calculations, your calculations section of your report. And don't forget to watch this video. I'm going to post everything on Moodle in a few hours. So there's no question. I'll call it a day. It's been 3.5 hours already.
Oh yeah, fun.
3.5 hours.
Yeah, it was.
Good. I'm glad that you guys enjoyed. All right, guys. Then
Yeah, well-
feel free to call me instead of emails. I prefer phone calls. It's straightforward, easy to answer. So if you have questions, call me.
Sounds good.
All right. See you guys next weekend then.
All right, thank
Alrighty.
you.
Bye-bye.